Okay, we are 3 minutes past, so we're just gonna kick this off. Hello, everyone, and welcome. My name is Alan Murges. I'm a consulting reservoir engineer here in Australia, and I'm also the founder of CrowdField, a digital ecosystem for oil and gas professionals to come together, collaborate, upskill, develop tools, and monetize their expertise. This session is part of a webinar series where I sit down with experts in their field and we discuss an interesting topic. So today it is my pleasure to welcome Steve Cuddy. Steve needs little introduction. I'm sure you all know him. Steve is a renowned petrophysicist with 50 plus years of industry experience. He's the inventor of the BBW height function, formerly with Schlumberger, BP, and Baker Hughes. He holds a PhD in physics and, if that was enough, in astrophysics and philosophy as well. He's the recipient of the SPWLA Distinguished Service Award, and he's known for challenging the conventional thinking in reservoir modeling. So we're set for a very engaging discussion. If LinkedIn is any indication, we should have a lot of people chipping in at the discussion we're going to hold at the end of the session. So just to keep things tidy, think of a session about 40 to 45 minutes and a Q&A session at the end between 15 and 20 minutes. So please stay muted throughout the session, again, just to remove the noise. And if you have a question, please raise your hand with a little hand icon you see at the bottom of your screen and wait for my cue before you unmute yourselves. Now, the session is being recorded for later distribution, and we'll also be sharing the PDF with the slide deck. With that out of the way, I'm just going to allow screen sharing and the microphone. So, Steve, feel free to share your screen now.
Can you see the first slide?
We can see the screen and we can hear you loud and clear, so just take it away, mate.
Right. So I'll just turn on a magic pointer so I can point at things here, right? I'm not going to read this, but these are the concepts we're going to review today. And as I said, they will be all in the PDF, so you don't have to take copious notes. You will get the information afterwards. Just have to listen, and I'll be happy to answer any questions at the end. So it's all to do about making a reservoir model. Today we're going to be talking about a 3D static reservoir model, and this is showing you an illustration of what one looks like. It looks like a Lego model with different colors for different bricks, and this is what we're trying to build. And they're very difficult to build because we've only got very limited data from the well locations, consisting of pressures, formation pressures, core data, and electrical logs. And this is very limited and is only available at these well locations. And we've got to initiate this model with hydrocarbons and water. And then when we've done that, we can use the model to calculate the oil in place, and we can use the model for well placement. Now, many of you must have seen this. This is a geology field trip where the team goes out to look at outcrops as they're cutting through the rocks here, and we've all been there. And what is amazing about this, what we see is that the structure of the rock changes dramatically from 1 inch to the next inch. The grain size, obviously the permeability, the color, and everything. And with complexity like this, how can we build a 3D reservoir model that represents a field of hundreds of cubic kilometers when we've got a very when we see this close up? So that's what we're going to explain tonight. So to do this, we've had to access certain common reservoir definitions. We've got water saturation, 0 to 100%, air against capillary pressure. Capillary pressures, as I'll say, can be converted to height above the free water level. And this is represented by the free water level at the base here, which I will explain very carefully. The oil-water contact is shown here. And then an interval which is called the irreducible water saturation, well above the free water level. Now, the definition says that there's a transition zone between the oil-water contact here and the top of the transition zone. If you didn't understand that, don't worry, because most of it's rubbish. These concepts are widely used, but I want you to think, do they really exist? We're going to go back to basics. So the only thing that exists in your reservoir is the free water level. If you drill a well where you're standing right now, eventually it will fill up with water to the free water level. This word is called free water level, which means the water below this level is free. That is throughout the presentation. It is free water below the free water level. In this well in your room, we've got air above it. So we've got interface between water and air. Now, in the oil field, the free water level is between the water and the oil or gas in the reservoir section. So we're going to review these common definitions. And we're going to do that by looking at the capillary pressure theory, the rock physics behind it all. We're going to look at actual electrical logs, density, neutron, resistivities, to see how it matches up with this model. We're going to look at core data. Core data is very important when we're doing petrophysics. And we're going to look at formation pressures, as I will show you next. The free water level is the intersection of the oil and water pressure gradients as shown on the left-hand side. So you've got the free water level. Above that, we have an oil gradient. Below that, we've got the water gradient. The water gradient is in the free water area. The formation pressure tool only measures the mobile phase. The mobile phase above the free water level is hydrocarbon, oil in this case, and below the free water level, it is water. So the free water level is where the oil and water would separate out in a very wide borehole, as shown in the cartoon on the right. That is a free water level. That's everything is derived from this definition. We must say that the water has got remarkable properties. As you all know from high school, the water molecule is made up of 2 hydrogen atoms and 1 oxygen atom. But you probably not realize, well, not everybody's realized, that the water molecule is polarized with a distinctive oxygen end and a positive hydrogen end, which causes the molecule to have a V or boomerang shape. This causes the water molecules to be strongly attracted to each other and to the reservoir rocks. And this is why the water, understanding the water in the reservoir is the key to understanding the reservoir. Just to say, the electrostatic force here is 10 to the power of 36 times greater than the gravitational force, which will be important, as I'll show you. Now, the water was in the reservoir first. Hydrocarbons, the oil, migrates into the trap, and a buoyancy force is exerted between the oil, which is lighter than the water, and it pushes the water down to the free water level. So we've got oil above water. Now, not all the water is displaced. Some of it is held by capillary forces, those electrostatic forces, which make water remarkable. So it is held by the capillary forces in the pores. Those who work with rocks realize that the narrow capillaries, pores with smaller pore throats, have a much larger surface area. And because of this, because of the larger surface area, they hold onto the water the strongest. And the oil is relegated to the middle of the pores. So let's have a look at the gradients arising from this one concept of the free water level. There is capillary-bound water, which is a continuous column of water within the oil leg, shown by this dotted curve, which is an extension of the hydrostatic water gradient in the free water below the free water level. So there is the gradient by the water. And this does exist inside the reservoir, although we do not see it with the tool directly, because the tool measures the mobile phase, which is oil. So the oil remains in the pore space, but also as a continuous phase, but a lower pressure gradient, as shown here. Now, the key point here, there is a difference in pressure between the oil and water phases, and this is called the buoyancy pressure. This is what happens above the free water level. The buoyancy pressure increases with height above the free water level. The capillary pressure increases, the buoyancy pressure, the difference, increases with the height above the free water level, displacing more water from increasingly smaller pores. Now, these two gradients, as you know, intersect at the free water level. So we can determine the free water level, preferably by measuring the gradient in the water leg and in the oil leg. The formation pressure tester only sees the mobile phase. Now I want to introduce another concept here, and it's called the bulk volume of water, BVW. It is simply the percentage of water in a unit volume of rock. Now, BVW is as you know, is the product of porosity and water saturation. This is water saturation, but we've moved away from water saturation and concentrating on BVW. Why we want to concentrate on BVW? Because all there is BVW. BVW is what is actually measured by the electrical logs. It's measured by the resistivity tools, the conductivity tools. It's measured by the hydrogen log and the density log. It is also what is measured by core analysis. Core analysis does not measure water saturation. If the client wants water saturation, then you take BVW, you take porosity and divide by BVW to get water saturation. So electrical logs and core analysis do not measure SW directly. And this means that BVW is much more powerful, as I will explain. So what are the forces then acting on the reservoir? The forces are acting on the water and the oil, so that the water at a given height in the reservoir is determined by the balance between the capillary forces holding the water up and the force of gravity pulling the water down. Oil is the only mobile phase and occupies the pore volume not held by the capillary-bound water. So we've got capillary-bound water above the free water level, and where it doesn't want any of the pore space, that pore space can be filled with oil. The water is around the edges of the pores, giving this electrostatic force. The oil is in the center of the pores. So they're very different locations for these two fluids. As the height above the free water level increases, the buoyancy pressure increases. So as we go above free water, this increases, and the volume of water is forced out of smaller and smaller pores, and so BVW, as shown here, decreases. Oil increases, BVW decreases. Oil is the mobile phase, water is the immobile phase, as I will explain later. As I said, we can get the free water level very precisely by good formation pressure measurements as the intersection between the oil gradient and the water gradient. You can also get it directly from the resistivity log. The resistivity log is also mistermed because really it's the inverse of the electric conductivity of the water, BVW. So we measure RT. As BVW decreases with the height above the free water level, the resistivity increases, or the conductivity decreases. The RT actually flatlines below the free water level. It is increasing here. There are obviously some shale effects shown in green upon the resistivity, but it is increasing with height, and below the free water level, it flatlines. So this RT can also give us an indication of the free water level. So let's have a look at the first concept, the irreducible water saturation. Irreducible water saturation is defined as the lowest water saturation that can be reached in a rock sample by removing water. This can be done either by flowing hydrocarbon through the rock and replacing it, the water, or a better way is to spin it in a centrifuge. In both cases, this simulates being higher above the free water levels. As we go away from the free water level, the capillary pressure increases. And we can reproduce this in a centrifuge by spinning a core. And by spinning it faster and faster, that represents greater and greater height above the free water level, and more water is expelled. Now, if we plot water saturation against capillary pressure from the centrifuge, or by removing the water by flowing hydrocarbon through it, we get this shape, but it doesn't come down to a minimum. SW irreducible depends upon the applied pressure or the centrifuge speeds. This is equivalent to moving higher and higher above the free water level. Logs, core, pressures, and capillary pressure theory tells us a minimum SW irreducible does not exist in practice. Maybe you've got software you use which asks for an SW irreducible, well, we'd have to get around that. But there is, in practice, we can go, there is no limit to where we go. It comes asymptotic to zero. So SW reduces indefinitely. Now let's talk about the oil-water contact. The oil-water contact is defined as the depth at which the buoyancy pressure becomes sufficient for oil to start displacing water and entering the pore space. I've got you a real log here to show you. On the left-hand side, we've got the water saturation, conventional scales, 100 to 0, porosity. The solid line is the low porosity. The dots are core porosity, so we've got a good match there. And in the CPI, we've got shale, only a little though. We've got sandstone, and we've got oil, as shown in red, and we've got water, as shown in white. So the oil-water contact is where the pressure is sufficient for the oil to displace water and enter the pore space. At this depth, SW drops below 100%, as you can see here at free water level. We get to this point, the SW drops 100%. That will be an oil-water contact. Also important to realize that BVW, the white curve here, becomes less than porosity, which is the line between the sandstone and the fluids. So this definition leads to several oil-water uptoes and oil downtoes in the well, but never an oil-water contact. So look at this. At the base, as we go above the free water level, we get to a point where the oil can start entering. Basically, the porosity is dropped to a level that allows the hydrocarbon to enter. So this is a oil down to here, but then we continue up a little bit further the well, and we get SW 100% again. We get BVW being equal to porosity. So this is not an oil-water contact. This is just an oil up to. Similarly, you get oil up tos, oil down tos, oil up tos because of this. There is no oil-water contact. Logs, cores, pressures, and capillary pressures tells us that an oil-water contact never exists. Now let's consider it did exist in our reservoir model, which we're going to use to place wells, and we're going to calculate the hydrocarbon in place. Say there was, at this depth here, we could work out what SW was. Remember, on the outcrop, a few centimeters away, in X and Y directions, the rock is very different, and you won't have an oil-water contact. It is dependent on the porosity. So an oil-water contact never exists. So if there's no irreducible water saturation, as I showed you before, and there is no oil-water contact, the transition zone is actually the entire reservoir, all the way from the free water level to the top of the reservoir. If somebody says they have a transition zone, they have an oil-water contact, they have irreducible water saturation, ask to see the logs that prove that. Ask them to show from rock physics and capillary pressure theory how they're derived. Now, let's look at another concept. Does water saturation depend on permeability? Well, if you look at the plot, I'm showing the same plot, so I don't have to describe it every time. We've got permeability on the right-hand side, permeability going from microdarcies to multidarcies permeability. And you can see it varies a lot. And what you see is that it's a mirror image of the water saturation, where we've got low water saturations, we've got high permeability and vice versa. So you would say, well, the water saturation must be dependent on the permeability. But this is not correct. This apparent correlation arises because both are dependent upon porosity. So permeability depends on porosity because it's dependent upon the porosity, the grain size, and pore geometry. SW is defined as BVW over porosity, so we got BVW, and if we divide by porosity, we get SW. So both of them depend upon porosity. SW changes with permeability, variability, whereas the BVW changes smoothly with height. So we got water saturation varying dramatically, but BVW changes very slowly and is independent of the shales and especially independent of the porosities. So remember, water saturation does not depend on permeability. Correlation is not causation. Another question people ask in the reservoir model, does mobile water exist above the free water level? Well, there are two types of water actually above the free water level. Two types. The first is the immobile capillary-bound water, which has been there for tens of millions of years, ever since the reservoir was first filled. And this water is sticking with the electrostatic force, that massive force, to the sides of the pores. Now, there's a second kind of water that we know exists in reservoir, which we don't like. This second type moves through the center of the pores, and this comes from water floods, coning, and when it reaches the wellbore, sadly, it causes water production. So there are two kinds of water above the free water level. The immobile capillary-bound water on the side of the pores, and the water that travels quickly through the center of the pores after production has started. But before production has started, there is only immobile water. The capillary-bound water doesn't want to move. If it could, it would have replaced the lighter oil. And take a break while somebody switches their microphone off. Yeah. So the capillary-bound water doesn't move. It's held by that fantastic force, right? 10 to the 36 times greater than gravity, trying to pull the water downwards. If the water above the free water level, remember the definition, free water level, if it was available to move, it would have been replaced by the lighter oil in the millions of years since the reservoir was first filled. Now, the formation pressure tool, as shown here, intersecting out the free water level, only measures the mobile phase. Formation pressure measurements that always show us, and they always show a straight line above the free water level. They only show the oil gradient. They only show the immobile fluids. Now, clearly, if enough drawdown was applied to this water, it would move. The capillary-bound water would eventually move, but the well would prefer to take the water from coning or from water flows because that is in the center of pores and moves easier. But it will move the capillary-bound water if you apply enough pressure, enough drawdown. If you apply a fantastic drawdown, the formation itself will move. And this is called sanding. Now let's move to another important concept, relative permeability curves. Relative permeability curves describe how two fluids flow simultaneously through a reservoir rock. And you may have seen these plots showing the percentage of water and oil that is moving simultaneously through the reservoir towards the borehole. Relative permeability curves are very important for the dynamic model, but not for the static model. They are essential when both fluids are mobile, like here, at the same time, such as during water injection, water breakthrough, or water coning. The mobile water that flows through the center of pores is fundamentally different from the capillary-bound water, which adheres to the pore surfaces. So the relative permeability curves are very important, but they can't be used to pick the transition zone, irreducible saturations, or the oil-water contact. If anybody claims they can do it, let them explain. Now, we need to populate our model with saturations of water and oil. And conventionally, we have always used a saturation function to do this. And this assigns oil and water each of those Lego cells in the model. So we need an SWI function to do this. And to derive the function, we need to look at the data to derive a function. So this is what we do when we plot water saturation in a field against the height above the free water level. We get a scatter, a shotgun scatter. Now, the different colors represent different porosity ranges. The highest porosities, over 16 porosity units, are shown in red. These are off to the left, and they come asymptotic to the free water level eventually. In the middle, we've got some poorer rock, shown in blue. These are actually fluvial sandstones. And then we've got sandy Sabkha sandstones on the right. And these have got lower water saturations. And as we expect, these are off to the right. There. And also SW is fully water saturated for hundreds of feet above the free water level. So how can we use this information to derive an SWI function to initialize, to populate our model with fluids? So what I'm going to do now, I'm going to replace the x-axis with BVW and see what we get. There we are. Remember, BVW is the percentage of water in the porosity, or it's the volume of water in a unit volume of rock. So replace the water saturation with BVW, and you can see the different types of rock, the aeolian sands, the fluvial sands, the sandy sabkhas are all intermixed because BVW is independent of rock type. And it's also independent of porosities, as showed you on that plot before, and independent of permeability, which makes life easy. So the SW shotgun pattern has collapsed to a simple function of BVW, bulk of water versus height. Now, this is the BVW function. This is probably the only equation I'm going to show you. It's BVW is equal to AH to the power of B. A and B are constants. H is the height above the free water level. Sometimes the BVW function is also called the fractal functions because it's derived from fractals as it's explained in the paper. Sometimes it's called the FOIL function, and sometimes it's called in Malaysia, they call it the Cuddy function. Don't know why. So this is the equation which is going to describe your model. So the BVW assigns water and oil to each of the reservoir model cells. The function is independent of phase type, porosity, and permeability, and all the reservoir is completely described by just two parameters. Remember the complexity we see at those outcrops, but we're going to describe it with just two parameters, or maybe less. This is a study that I did with a number of core analysis friends, Craig Lindsay and others, and we looked at a number of wells in the North Sea, a number of fields in the North Sea rather, and these fields were very different. They had different geological age, they had different types of rock, carbonate, sandstones, and they had different pore fluids. They had some had gas, some had oil. And what you notice is the BVW function is a straight line. This is because it's an exponential, as I showed you before, that exponential top there. When you convert to log scales, you probably remember from your school, this turns into a linear relationship, as shown here. Now, when you plot the core on these log scales, what you notice, they all fall into simple lines. So each of these fields is represented by a different color. So in actual fact, each of these lines, these BVW functions, can be described by two parameters. We could have just taken two core plugs from each of these fields and derived these BVW functions. We could have saved lots of money. We're doing less coring by just taking a few cores. But it gets better than that. So we're saying only two valid core or electrical log measurements are required to calculate the intercept A and the gradient B. So you can do this from core, as shown here, or you can do it from logs. But notice something very interesting here. All the gradients are identical. They've all got a gradient of 0.42. So really, we can describe all fields in the North Sea by one parameter A, because the other one is always 0.42. The answer is 42. So let's go back to SW again. This was petrophysics' greatest blunder. It was to invent a petrophysical term called water saturation, which complicates everything. This is water saturation as we see it. It's varying all over the place. It's affected by these shale beds here. It's inversely proportional to the porosity. Now, all tools, resistivity tools, conductivity tools, all logging tools detect volumes. They do not detect percentages. Borehole logging tools don't measure SW directly. They measure the conductivity of BVW, as shown here. And BVW is ignoring the porosity, and is a very simple function of height because of the change in pressure there. So logs and core prefer to talk in BVW space, and this makes life easy. You don't need a geologist. So as I said, the core analysis doesn't measure SW. It measures the BVW expelled from rocks by forcing oil through it, or you put it in a centrifuge. And this represents different pressures, and the different pressures represents different heights above the free water level. BVW is decreasing with height. SW confuses things because not only is a percentage of a percentage, and remember, if you try and combine percentages, strange things happen, but it also increases uncertainty. How does it do that? Well, if you want SW, you need a resistivity tool, which is measuring cubic meters of rock to calculate BVW. And then you have to have porosity, which is measuring cubic feet of rock. So you bring in two different units together, and this increases the uncertainty in the hydrocarbon in place in our model. BVW is independent of porosity, permeability, and rock type. Makes life easy. So I'm showing you with the arrows here. This is the water saturation varying, and this is BVW constant. So it's best to forget SW completely and instead use a volume-based measurements like BVW. Let me tell you more. So the first question people ask is, well, if we don't have SW, how do we calculate the oil in place? The reservoir model is initialized with porosities and BVWs using the BVW function. It doesn't use SW. It's populated by porosity and BVW. Each of these cells is averaged for porosity and BVW. You can average a porosity easily by adding together and dividing by the number. You can average BVW easily. You cannot average SW easily because it has to be pore volume weighted. So just stay in BVW space. Oil in place is therefore just a sum of all the cells by taking the BVW from the porosity. And that's the oil in place. SW is not required. SW just adds uncertainty. A J function is required, but I'm a consultant. The client often asks for a J function and a BVW function. I always give them both and charge them twice as much. So let's look at another concept as we're getting towards the end of the presentation. Should we use total or effective porosity? This would be a presentation in itself. It's one of the big debates in petrophysics, but I will give you the conclusion slide from that presentation because it is quite straightforward. Let me remind you, there are petrophysicists confuse things by defining two porosities: total porosity, which is the effective porosity plus the clay-bound water. Total porosity is effective porosity plus clay-bound water. So they've got two porosities. First thing I would say in the other presentation, the density porosity is irrelevant here. The density porosity is not total porosity because the density porosity measures somewhere between the two. But now, if the core data was available to was available, core data often measures the total porosity. So we can get a direct measurement of total porosity from the core data. And then we can derive phi E, the effective porosity, by taking away the clay-bound water. So I'm saying you should calculate both of these, total porosity and effective porosity, and charge the client twice for two things. But the thing is, as you notice in the reservoir model, if you use phi T with SWT or phi E with SWE throughout the model, they will both calculate at the bottom line the same hydrocarbon pore volume, because the hydrocarbon pore volume is a difference between the porosities and the BVWs. So provided you're consistent to use total throughout or effective without, it doesn't make any difference. So this debate is not important. Also, the BVW function, which you're going to populate, initialize your model, as shown here, it only requires 1 or 2 points, and you pick this 1 or 2 points from the cleanest sand, so you don't have to worry about the clay-bound water. Now, even though you're not worried about the clay-bound water, the BVW function is valid from everywhere, from the free water level to the top of the reservoir, because it's independent of rock type, including the shales. So I could give that presentation another time on effective and total porosity. So, question mark, are these reservoir modeling myths? At the bottom of your garden, some people claim they've got fairies. But they claim they've got fairies, but they claim they exist, but they fail to provide the evidence. Similarly, some reservoir engineers and some petrophysicists claim there is an oil-water contact, a transition zone, and an irreducible. But capillary pressure theory, electrical logs, core data, and formation pressures say they do not exist. But it's a question mark, so I'm leaving it up to you to decide. I'm just saying, think about it. Can you use any of these bullet points to prove any of these fairies, these myths exist? So, in conclusion, the free water level is the only reservoir concept that you really, really need. It's where the water would separate out in a wide borehole. And it is defined by the intersection of the pressure gradients above and below, or from the end of the resistivity log. So, based on that, is SW irreducible, the oil-water contact, and the transition zones myths? As I say, it's up for you to decide. You have to talk to the client, right? Do you want to complicate things by having these things? Now, does mobile water exist above the free water level? Yes, it does. But after production starts, the water comes from elsewhere. It comes from coning, it comes from high permeability streaks, and it's a real pain, right? But the day before you produce the well, there is no mobile water above the free water level, because if there was mobile water, it would have been replaced by the lighter hydrocarbon over the hundreds of thousands of millions of years since the field was first charged. And you can prove this with the formation pressure tester. The formation pressure tester sees the mobile phase, and if you run it from the free water level all the way to the top of the reservoir, it only sees an oil gradient. How about relative permeability curves? They are very important. They're important for understanding the dynamic model, but they're not required for the static reservoir model. We've got you get displacement of one fluid by another, not two fluids moving simultaneously. In the phi T, phi E debate, you should calculate both, but both of them will give you the same hydrocarbon in place. One will give you a check on the other. So it doesn't really matter which one you use in the model, provided you're consistent throughout. So the final conclusion is, forget all about SW. All of petrophysics could be done without SW. Because SW is percentage sorry, it gives some more uncertainty. Anyway, instead, think volumes. Think BVW. Thank you. And I'm open to any questions.
That was great, Steve. Did not disappoint. Lots of concepts, lots of food for thought. So I'm just going to open up the Q&A. Please, guys, raise your hand with the little icon before unmuting yourselves. Just wait for my cue. I'm just going to kick off the Q&A with a first question myself, Steve, if you don't mind. With regards to the irreducible water saturation concept, so as you mentioned, as we move up from the free water level, we increase capillary pressure, saturation goes down, water saturation that is, and in theory, we could keep increasing capillary pressure to infinity and keep reducing the water saturation. But in practice, the pores are not perfect spheres. The rock has a very complex topology. So as you increase capillary pressure, you push the water towards the corners of the pores. You keep pushing the water more and more towards the corners, and eventually you might get to a point where the water actually becomes disconnected. It's not continuous anymore. Isn't that, in a very practical sense, the point below which you cannot keep reducing the water saturation? Therefore, there is indeed a very practical irreducible water saturation when you reach that point. What's wrong with that view?
Yes, Alan. This has been brought up by a number of co-analysts, reservoir engineers, and that as you increase the capillary pressure and you force more and more hydrocarbon into smaller and smaller pores, the water saturation is going down, but it doesn't remove completely because it stays in the crevices and that. But it's discontinuous, so you wouldn't see it on the resistivity log. But also, more importantly, it's going down so far. You must agree, it's less than 1%. So if it's less than 1%, why can't we just say it decreases indefinitely? Alan, have you got an idea of an irreducible water saturation because of this feature of the pores at great distances from the free water level? Have you got an idea what SW irreducible could be? And have you got evidence of getting this by centrifuge experiments? Have you got evidence of this by looking at pressure plots? Where is the evidence for SW irreducible reducing below 1%?
No, that's fine. So it's just a question in principle. So I get your point. So yes, in principle, there is a point in below which it becomes disconnected, but it's just so finely confined to the crevices and corners. There's a very, very minor value indeed.
I'll accept that. Good point. Very good point.
Okay. And the other one before opening to the rest, I'm interested in the zone between the free water level and the all water contact. However meaningless that term is, there is a point above the free water level where a threshold pressure or entry pressure is needed to displace the water and for the oil to enter. So by definition, there is a zone between the free water level and that contact where there is only water in the system. So water is 100%. But you say that the water is immobile above the free water level as indicated by pressure measurements. But you say that above the free water level, water cannot move. So what is it that a pressure records in that zone? It cannot record an oil pressure gradient because there's no oil, and it cannot record a water pressure gradient because you say the water is immobile above the free water level. So what is it that do we have? And do you recognize that the oil gradient assigned to this place is basically just a down extrapolation from the gradient sitting above?
Right, Alan. Can you see this plot here? Can you see it? Right. So the interval we're talking about here is between the free water level, free water below that level, and to the first point here where SW drops from 100% and BVW is no longer equal to porosity. This interval here. In this interval here, if you run a formation tester, you would get tight points. You wouldn't measure a water gradient or an oil gradient. You wouldn't measure either, right? But hypothetically, if you see, you're talking hypothetically, if you actually caved out a large piece of rock here, like a pothole, and you filled it with silicon, and then you took the formation tester down there to that point and measured the pressure, what would you measure? The pressure of water, oil, or silicon? You would measure the pressure of oil, because there's a vast amount of oil supporting the silicon in there. So between the free water level and the supposedly oil water contact, the first one is here. It is impossible to measure a pressure from the formation test, MDT, right? But if you've got a little kink of rock here where there is some porosity, and you were able to get a pressure, that pressure would be oil density pressure. So the oil gradient extends from the free water level to the top of the reservoir. But I accept there are intervals which are tight, which the tool is incapable, or you'd have to sit around for many days to get the pressure. So that's right.
So that's interesting. So if I heard you correctly, you say that even in that zone, you would record, if you could record, you would record an oil pressure points, even if there is no oil. Is that what you just said?
Yeah, even there's no oil there. But remember, the rock changes dramatically. A few feet away, left and right from this, in the real world, you will get a better piece of rock. You can see how the sandstone is varying dramatically vertically. It's also changing dramatically to the left and right. So to the left and right, you move a few inches, you will get a piece of rock with a porosity which is full of oil.
For sure.
Even though this is a water interval only in this well. This is why the oil-water contact is a meaningless, not useful concept when we're talking about 3 dimensions.
For sure. Okay, thank you, Steve. I'm just going to open up now. So Harold, take it away, mate.
Yes, Harold. Yes. I think we've spoken a lot on LinkedIn. Have you got a particular question?
Harold, yeah, you got your hand up, mate. You need to unmute yourself. Okay, Jamal, you can take it away now while we wait for Harold.
Yeah. Hi, can you hear me well?
We can hear you, yeah.
Yeah.
Hi, Steve. Thank you for the great presentation and sharing session. My question is about fractured reservoirs, where we have secondary porosities, fracture-related porosities. How do all these concepts apply to fractured reservoirs?
Very good question. When we've got different kinds of pore structures. We've got some wells. We've got dual porosity, and other wells we've got fractures, and these contain lots of water. Well, we've done many BVW functions on these fields, and BVW function works quite well in fractured reservoirs. And all you need to do is use a very powerful petrophysical tool, and that's called the cross plot. And you plot on your cross plot your water saturation against height or capillary pressure, and on the z-axis you color it by a recording of whether it was a fracture point or dual, what kind of porosity you've got there, and then you make another plot where you use BVW, and you see whether it collapses. And if it collapses, then as we've always seen, then BVW is appropriate for those kind of reservoirs. So I don't have to give you a theoretical answer. You just make a cross plot and see what it does. Presumably, you can identify all the core plugs by whether they've got fractures and cracks in them and different porosities. Yeah, good. And I'd be happy to look at that for free, because it could improve this presentation.
Thank you.
Okay, we're just about out of time. Harold, I see you rejoined the meeting and you had your question up before. Do you want to go ahead with your question, Harold? No? Okay, seems like the audio is failing on Harold's side.
Well,
if there's no one else who would like to take the mic up, anyone else? We're just past the hour. Nobody else? Okay, Gareth, take it away.
Hi, Steve. I've come across cases before where we're looking at carbonate reservoirs, like places like the Hough, where you see is predominantly dolomitized, but then you get small intervals of higher porosity limestone, poor permeability. So we don't see that diagenesis sort of occurring. And I found in those cases we do actually have to have a different saturation and height function for those local intervals of basically limestone within a predominantly dolomitic interval. So I mean, I think this is a case where you could say that actually the BVW is dependent on rock type, because you will find different rock types locally within some of these carbonates, these complex carbonates.
That is right. In many fields, it's been said that they can see a different BVW function by rock type because of very specialized rock types. Whether you believe that or not, the point is you need to populate your reservoir with those rock types before you can apply your function. There's no point in saying I've got dolomitic and I've got different kinds of rocks in my reservoir unless you can map them with confidence in 3D. And I would say just use the basic BVW function, the one based on total porosity, and that is calibrated to core porosity, and see how well that does. And if you can tweak it, then we will get a better reservoir model, and me and you can write a paper on it.
Yeah, I'd just like to say that the BVW versus height has actually saved my life once before. At least once before,
Right.
Where we had no MICP within the calcite intervals.
Mm-hmm.
Ali, you have your hand up. Take it away.
Hello, everybody. Hello, Steve. Thanks for your presentation. Did you hear me?
Yeah,
Yes, I can hear you.
If possible, I want to add something about the last question. I think it was a good question that in carbonate we may have more than one PVW function. We know we have some work with the Steve, we know about it. But in carbonate, I think it's better to say that in the genetically related pores, it could be a good definition for that. In genetically related pores, for example, as our friend said, that in dolomite with genetically porosity is based on dolomitization, or based on phase selective, or based on the dissolution, or based on sequence stratigraphy. So each kind of porosity or genetically related porosity may have a bulk volume, another bulk volume curve. But the most important one, as I know that Steve is the perfect to say about this, is that the BVW reduce the rock type we need for the formation. In very complicated formation we tested, we get from more than 6 rock type to just two rock type to describe the all formation, just by two bulk volume functions.
Mhm.
Yeah. Thank you.
That's good. Yes, I agree. BVW does simplify it, and if you do simplify it to two rock types, that is an advantage over simplifying it to 20 rock types. Yeah, Ali, I agree. And many universities start with BVW, and then they tweak it for their particular field.
Okay, I think we're just about out of time. I want to thank Steve for coming on. It was my pleasure to host you in this webinar series, Steve. Thank you very much. Thank you everyone for tuning in. I will be sharing the recording with the session and also the slide deck in PDF format. So just stay tuned. There will be an email to follow with these two resources. Okay, so thank you everyone once again. Have a great day.
And I'll answer any questions afterwards, yes, as well.
Yeah, we can keep the discussion on LinkedIn for sure. Thank you, Steve. Thank you, everyone. Have a great day.
Thank you.
Thank you.